Now we have reached 2 o'clock here in Denmark, so it's a pleasure to welcome you all to this webinar about creating 3D inversions from 2D datasets. And I'm doing today's webinar as a pre-recorded webinar. That means that I recorded it in advance, and then I'll start the recording in a moment, because then I have time to answer any questions you might have during the webinar in the Q&A session and in the chat. Then after the webinar, after the pre-recorded part, I'll go online again and follow up on a few of the questions if there are any questions of general interest. And then we will also post a document with answers for all questions during the webinar on our webpage, together with a recording of the webinar in a few days when we have had the time to edit it. And you will then be able to find it on aarhusgeosoftware.dk under the webinar sessions. And there you can also find all of our previous webinars if you want to watch any of them. So then I'll just introduce myself. My name is Knud Valdemar Lassen, and I'm a geophysicist at Aarhus Geosoftware. So enjoy, and remember that you can always ask questions in the Q&A session and in the chat. Then I'll do my best to answer them. Hi, I'm Knud Valdemar from Aarhus Geosoftware, and in today's webinar, we'll talk about how you can combine normal 2D resistivity survey lines into a 3D dataset for inversion in Res3DInv. And the program we will go through today is a short walkthrough of the different types of 3D and pseudo 3D datasets that exists and that you can create. Then I'll tell you how to actually combine these 2D datasets into a 3D dataset. There's some functionality in Res3DInv that can help you do this. And then I'll show you how to actually do it in Res3DInv. Then I will talk a bit about the pitfalls when combining 2D datasets into 3D datasets, some of the things that you have to be aware of. And then I will show you an example of a 3D inversion made from 2D lines. And finally, I will talk a bit about an alternative to doing 3D inversion, and that is interpolating 2D inversion results into a 3D model. And I'll talk about when this is a good idea and when it's not a good idea. And then I'll show you an example of how to do that in our software Workbench Essentials. And most of the stuff I'll talk about today is following the course notes that Dr. Loge, the original author of Res2DInv and Res3DInv, have made, especially chapter 8, which is called the 3D electrical imaging surveys. And the notes can be found on the link shown down here. And after the webinar, we will publish a document with answers for all the questions that we might receive during this webinar. And in that document, I'll also put a link to this to these course notes, so you can find them afterwards. And we'll also put a link to some other literature. And finally, I want to say that you are very welcome to ask questions during the webinar. You can do that in the Q&A session. And then I will try to answer some of the questions after we are done with what I have planned today. And if there are some questions that I cannot answer on the fly, so to speak, then as I said, we'll put the answers out in a PDF that will be published on the Aarhus Geosoftware website in a few days. Okay, so let's get started. I'll start with a little walkthrough of different kinds of 3D dataset, if you can say so. And I'll mainly do this to shine a light on some of the compromises we make when creating a 3D dataset from 2D surveys instead of making a what we could call a true 3D dataset from the beginning. So I'll start with this true 3D dataset, which I have also called the ideal 3D dataset. So this is a dataset where the electrodes are laid out in a grid, and this can be more or less structured depending on the field conditions. And then we simply do measurements in all imaginable configurations in all different directions. So we can make a measurement using electrodes from all lines in both directions of the grid. And the advantages of this kind of data set is that it covers all the possible current paths in the ground. So you don't only have the current running along the 2D lines, you have it running in all directions through the ground. And this gives you the most ideal resolution of 3D structures. So this is really as good as it can get with the 3D datasets. The drawback is that it is very expensive in both time and equipment, because you need a specialized 3D equipment that can address all electrodes in a grid independently of each other, and you need to spend a lot of time setting up this grid with electrodes in all directions. And you also need a lot of equipment because you need to have access to all the electrodes at the same time. You cannot just make the measurements line by line. Then we have the second best option, which I have chosen to call the best we can do with 2D instruments 3D dataset. So we have the same electrode layout as we have for the full 3D dataset, and then we make measurements in all directions along the grid lines, and also at some angles to the grid lines. So that means that we don't have all of these electrodes laid out at the same time. First, we'll take, for example, this line consisting of electrode 3, 8, 13, 18, and 23. Then we'll do measurements along that line. Then we'll put out a line in this direction and do measurements along that. And then we'll put out a line in this direction at an angle to the other lines and do measurements along that, and so on. So the advantage here is that we have nearly as good a data coverage as we have with the ideal data set, but this kind of survey can be carried out with what we call standard 2D equipment. The drawbacks is that it's possibly even more time consuming than the ideal 3D survey, because we have to move our electrodes and equipment around a lot to make this kind of measurements. So in reality, I don't think I have ever seen anyone carry out a survey like this to full extent. So we'll quickly move on to the realistic way of doing this. So of course you can have all stages between the ideal data set and the realistic data set, but I have just skipped a few, and now I go to the realistic data set. So these are the data that I will use as an example today. And as you can see, the electrodes are still laid out in a pretty much very structured grid. The electrodes are these red and blue crosses here, and this survey consists of some parallel lines, and then you can see that we have a few tie lines at different angles to the main lines. The pros in this case is that you still have decent 3D information, so you can still make a good 3D information that will give you more information than just carrying out the 2D inversions individually. The survey can again be carried out with standard 2D equipment, but you'll have to move the equipment around quite a lot, so it will still take a long time. But this is a good trade-off between resolution and price. And as I said, the drawbacks is that it's still much more time-consuming than just doing a regular 2D survey. And if you are unlucky, it does not provide as good 3D coverage as the ideal 3D dataset. For example, you can see that here in the middle of the survey, we only have lines in one direction. So if this had to be more ideal, then you would maybe add a few more tie lines to the survey. So to sum up, the two most important things to consider when creating a 3D dataset from 2D lines is to have a relatively low distance between the lines if you combine it from a parallel 2D lines. And the other important factor is to have lines in several directions. So how close is close together? Ideally, the spacing between the parallel 2D lines should be the same as the electrode spacing within these lines. But in reality, this is rarely the case. So if you look in the course notes that I linked to in the start of the video, there's a very thorough walkthrough of different array types and how much sensitivity they have beside the line. So how far away from the line the different array types have sensitivity. And it turns out for a lot of the configuration, it is actually acceptable to have up to 2 to 3 times the electrode spacing between the 2D lines. And then I have written lines in several directions. This is because when you add the tie lines, you can again allow the distance between the lines to grow a little. And in addition to that, instead of just having the current running in one direction in the ground along the 2D lines, then you have the current running in other directions as well, and that gives a better resolution of 3D structures in the lines. And you can see the data set that I have chosen today. This is a very common 2D to 3D data set, if you can say so. So it doesn't completely fulfill any of the criteria I have just mentioned. The distance between the 2D lines is 5 times the electrode distance, but then we have a few tie lines at different directions, kind of making up for that. And as I can show you later, we get pretty good 2D inversion, 3D inversion results out of this. And even without the tie lines, you can still get more information from doing the 3D inversion usually than you could have had if you're just doing the 2D inversion. That's of course also dependent on the subsurface. If the subsurface is very homogeneous, where you have neatly stacked layers, then you will not gain a lot of extra information from the 3D inversion. But if you have complex 3D structures, you should be able to see them in the 3D inversion much more easily than just looking at the 2D inversions. Now I'll move on to show you how to actually combine the 2D lines into a 3D data set. And for this, I'll use the built-in tool in Res3DInv. And the way to do it is to prepare the 2D DAT files in exactly the same way as you would for a regular 2D inversion in Res3DInv. And this includes maybe removal of bad data points and stuff like that. And then you combine the files using Res3DInv, and this is done by preparing a text file that tells Res3DInv where all of the files are and where you want the output file to be. And for this, again, there are two options. One option is to add the global coordinates to all of the 2D files, and then Res3DInv will use this information to position the files in the 3D file. So to position the 2D lines correctly in the 3D file. The other options if you don't have global coordinates for all of your 2D lines, if to define the relative positions of the 2D lines in the text file that you give Res3DInv, and then it will do the combination of the 2D lines based on that. The second option only works for perpendicular 2D lines like shown over here, whereas the first option works for 2D lines located in all directions. And generally, I will recommend using the first option because it is much harder to make mistakes in that one. So as soon as you have the correct global coordinates in the 2D files, then it's much easier to make the correct combination of them. Whereas in the other option, it's quite easy to switch around two lines and make one of the lines go in the wrong direction, stuff like that. So I'll just sum up how you add global coordinates to a Res3DInv dat file. You basically do that at the end of the file. So this is the last few lines of a Res3DInv dat file. You see the last data lines up here. And then we have a 0 here. You can also have the topography section here if you also add the topography. And then we have this header for the global coordinates. And then we add the number of global coordinates, and then we simply put the global coordinates here. So in this case, we have 17 pair of global coordinates. And then we have 3 columns, one with the local profile coordinates, so the distance along the profile, and then a column with the X and Y global coordinates. And then we end the file. So once we have added the coordinates, we are ready to create the text file that we give Res3DInv to combine the 3D dataset. And the text file look like this. It's pretty much self-explanatory. So you have some header lines, then you put in the number of data files to combine. In this case, you can see it's 12 here, but I have actually only taken 3 of the files with us down here so that we can fit it all on one screen. So you put the number of lines to combine here. Then you define the X and Y grid spacing for the 3D file. And a good starting value for this is usually the electrode spacing in the 2D lines. So in this case, 5 meters. And then you simply put the full file path and file name to each of the 2D files. And then finally you name the output file. So this is the file for Res3DInv. You also put the full path and the name of that file in the text file, and then there's this end of file tag at the end of the file. So this is how the file looks, except that I will actually have 12 data files here instead of only 3. And this was the option 1 that I recommend. So this is the option where it is required to have global coordinates in the 2D files. This is the other option where you don't have the global coordinates in the 2D file. So it's pretty similar, but you can see we have some extra lines. And these extra lines tell you the X and the Y location of first electrode along this line. So for each 2D line, you have to tell Res3DInv where is the first electrode. And then you have to tell if the file is in the X or the Y direction in the local coordinate system. And then there is the line sign, which means is this line going in the positive direction. So that is positive X or positive Y direction from the first electrode, or if it's negative, it means it's going in the negative X and Y direction from the first electrode. But apart from that, the file is pretty similar. Another drawback of using this method is that you have to manually edit the grid discretization afterwards, because when you use this method, you will have one grid node in the direction along the grid line, along the 2D lines. There you will have one grid node for each electrode in that direction, and in the other direction you will have one node for each 2D line. So if the spacing between the 2D lines is different from the internal spacing in the 2D lines, then you will get a skewed grid out of it. So generally, if you have the global coordinates accessible to you, I really recommend to use this option 1 instead of option 2. And now I'll switch to Res3DInv and show you how to actually combine the files when you have created this text file. So here we have Res3DInv, and then you simply select File, and then you select the Collate Data into Res3DInv Format option. And this will open a file menu, and then we select the file that we just created, or the file that I just showed you, containing these lines that tells Res3DInv where all of the 2D lines are and where to put the final 3D dataset. Then we just say open, and then Res3DInv will read each of the individual 2D data files and then combine them into a 3D dataset. And this takes a few minutes, so I'll just cut here and then get back to you when this is done. So now Res3DInv have written each of the 12 2D files, and the program will now create the 3D data file. And here, when you use the first option I showed you, you'll have the option actually to change the values you have put in for the X and Y grid spacing in the 3D file. And you'll also have the option to allow the program to use a non-uniform grid spacing. So if you have areas where there are not any electrodes, or the electrodes are spaced far apart, then it can use a wider grid spacing out there, and then the inversion problem will be a bit smaller and faster to run. So I usually say yes to using this option, and then you select OK, and then it tells you that the Res3DInv that file has been saved in the folder you specified. And I can just show you that this is the case. So here we can see combined 3D. That is the 3D dat file that we have just created, and here it is. So now I'll move on to starting an inversion with this and show you the inversion result. So here we have Res3DInv, and now I can just load the dat file that we have just created, called combined3d.dat. And you can see the file loads without any problems. We get this message telling us that there are 354 point electrodes that are closer together than one node spacing in the grid, but they are not used in the same array configuration. So this is okay. And we select OK, and then we're actually ready to run the inversion. So I'll just start the inversion here by saying carry out inversion. And then we have to specify where to save the inversion result. And as you can see, I have prepared an inversion in advance, so we don't have to wait for this inversion to be done. On this PC, which is quite a fast PC with a lot of memory, the inversion takes about 2 hours for this dataset, so obviously don't have time to wait for that, but I'll just start with inversion so you can see how it works. I'll just call this 2 here, save, and then the inversion has started. But I'll just quit it again and switch to the inversion results that I had prepared in advance. To load the inversion result I have prepared in advance, we'll go to the display mode in Res3DInv and say display results. And then we will load the INV file here. And then the good way to show the results are in the built-in 3D viewer in Res3DInv. So I'll just open that. And this usually takes a few moments to start up. Now the 3D viewer has opened, and I'll just maximize it. And you can see the inversion result here. You can see, which is very often the case, that we have some artifacts along the 2D lines in the first layer. This is pretty normal for most inversions made like this, but if we make a cut plane and just cut away the uppermost layer, you can see that this is mainly a problem in the uppermost layer. So I'll just do a volume cut here, and then I want to make it vertical so we can step down through the model. You can see the gray dots here, they are the electrode positions, and then I'll set the step length to 1. Then I'll try to step this all the way to the surface. Maybe I should set the step length to 5 meters instead. And then you can see that we have all these artifacts in the top layer. But as soon as we start to go down through the layers, then we don't see them as clearly anymore. And you can see here in the model, this data set is from an environmental survey in Denmark. So it's a high resistive background. So these are the reds and the orange colors you can see here. And then we have in green the low resistivity area, which is a plume of chemical pollutants, and you can see that it is actually mapped quite nice by this 3D survey. I'll just try to turn this back to 90 degrees so we can step through the model. And again, you can see here, I'm just starting from one end, stepping through the model. You can see the pollutant cloud as the low resistivity area in blue and green quite clearly. So this is actually quite a nice result for 3D inversion. Another feature I would like to show you in the 3D viewer is the thresholding feature. So it's just remove the cut plane here. Instead of looking at the data in slices, we can look at it in resistivity intervals. So we can say, for example, that we only want to see resistivities below, let's say, 50 ohm meters, and see how that looks. So now we see everything between 0 and 50 ohm meters. And again, then you can in 3D very nicely see the extent of this pollution. So yeah, this is how to go from a set of 2D data lines until a full 3D inversion of a resistivity data set. And then, as promised, I'll spend the last few minutes on showing you an alternative to full 3D inversion, which is interpolation of 2D data lines. 3D interpolation instead of 3D and inversion is a possible alternative when full 3D inversion is not an option. And this can be because you don't have the software to do it. you don't have the computational resources, the memory and the CPU power required to do a full 3D inversion of a given data set, or simply because you don't have enough time to make a full 3D inversion before you have to present some data, then a good alternative, or at least a possible alternative, can be to do a 3D interpolation of 2D inversion result. And this is most suitable for simple layer geologies, because when you do this, you are still only performing a 2D inversion. So there is no way that you will see the most advanced 3D features in this kind of interpolated models. But if you have a fairly simple layered geology that can be inverted well with 2D inversions, then you can get a decent result out of interpolating these 2D inversion results into 3D. And the steps to make a 3D interpolation of 2D results, at least in the Aarhus Workbench Essentials, which is the program I'll use for this example, is to run the inversions as usual in Res3DInv, then export the results to VTK files as described in the guide that can be found at this link. We'll also link to it in the document that we put out after this webinar. And then you import the VTK files into Workbench Essentials and perform the interpolation there. And then you can view the final result in the 3D viewer in exactly the same way as I showed you before. So now I'll just quickly run through this workflow for you, and then afterwards we'll have time for some questions. I will start in Res3DInv, and I've already performed the inversion, so the inversion result is ready. So I'll go to a display mode and say show inversion result. Then I'll load the inversion that I have already performed. And you can see I have performed seven 2D inversions here, which are the inversions I'll interpolate into a 3D result. So now I have just loaded the last of the 7 inversions. Then I'll go to File, Model Export, and then I will say choose Model Output in VTK file format. Then you can choose which iteration to export. Usually you will use the last one. And I select OK. And then I select where to store these exported files and what they are called. And now I have exported the results. And as you can see, it both exports a file called profile 7 3D VTK, and then one which is also called global.vtk. And the only difference between these two is that the one called global are in global coordinates, whereas the other one is in local coordinates, and we'll need the global version for this. So then I open Aarhus Workbench, and I have already prepared a workspace where I have loaded in 6 of the 7 2D lines that I'll interpolate here. So now I'll show you how to load in the last one and how to actually do the interpolation. And if you want to know more about creating workspaces and adding background maps and stuff like that, you can see I have already added a background map here. Then you can watch the webinar about working with 2D, DC, and IP data, which in Aarhus Workbench, which can be found on our webpage. But to load in the file that I just exported from Res3DInv, I go to the Workspace tab and select External Grid. And then down here you can import 2 types of grids to Workbench. Surfer grids, which are elevation grids usually, and then these VTK grids. So if you don't see any files here, then you have to switch to the VTK option down here. And then you can see all the VTK files that I have exported from Res3DInv. And then I'll need to select the last one, profile 7, global VTK. And then I just select open. And then I have to give it a name. And then I have to select the coordinate system. And this coordinate system is simply just the coordinate system that you put the coordinates in the original 2D DAT file in. In this case, it's UTM zone 32 north coordinates. I'll just select that. And then it is imported into the workspace. So now you can see I have imported 7 2D lines in this workspace. To interpolate them, I need to combine them into what we call a model selection. To do this, I go to inversion, and then I say new model selection here. And then I select the 2D grid options, and then I highlight all of the grids that I want to import. I just select OK and give it a name. I'll just call it 2D for interpolation here. OK. And then the model selection will appear over here in a moment. Here it is. And then we can check the checkbox next to it, and then you can see that the lines will actually be plotted on the map. I can just zoom in on them. So these are the 7 2D lines that I have just imported. Then to make a 3D interpolation of these, you go to the Visualization tab and select 3D gridding here. And then you give the grid a name. And then just load the models. And then you set up the interpolation routine. So first you set a search distance. So from each of these models, how far out do you want to search to find models? Then we set up the grid spacing in the grid. I'll use 5 by 5 meters like we did from the inversion. And then I'll have 10 layers. Maybe I'll actually have a bit more. 15 layers in the depth, and we can have linearly spaced depth layers, or we can have logarithmically spaced, where you then give the depth of the first layer only. And I'll use this option because that reassembles the discretization of the inversion most closely. And finally, you can select if you only want to do a 3D interpolation of part of our data area, but I'll just select the entire area. And then you select OK. And then it takes a few seconds to do the calculations. And then we can see that the 3D grid is in our workspace manager over here. And then to view it in 3D, I go to the 3D tab and create a new 3D view. Then we have an empty 3D viewer here that I can open. And then we just need to add the grid that we just created to the 3D viewer by highlighting it in the Workspace Explorer and select Add Layer. And then you can see we have added the 3D grid here. And the default color scale is 1 to 1000 ohmmeter. That doesn't fit perfectly with the data we have here, so I can just change the color scale. And you can either select one you have already created in advance, or you can edit it manually. In this case, I want to edit it, so I select Edit. And then you can see a histogram of the data on the plot. And an easy way to start is just to take the minimum and maximum data value. You can see then you'll get quite a long tail here where you don't have a lot of data values. So I'll just trim it a bit. Say I want a color scale going from 40 to 1000 meters. Yes. Then I select Finish and save the color scale. and select OK to use the new color scale, and then you can see we have a lot more of detail here. And like we could before, then we can start to look through the data in different ways. And you can see the result is not as impressive as a true 3D inversion, and this can both be because we of course have less information here because it's just interpolated 2D inversions, but there's always also room for playing around with the interpolation settings to get it just right. Okay, that was everything I wanted to show today. So now I have time for a few questions, and remember that in a few days we will both put the webinar, the presentation that I have made, and the links to all the resources that I talked about on our webpage, together with a document with the detailed answers for all the questions that we have received during the webinar. Thank you. Thank you for joining this webinar, and I have received a few questions during the webinar that I'll just try to answer the best I can now. The first question is whether this file I created for combining the 2D files into a 3D file is a normal text file or DAT file or what it is. And it's simply a normal text file. I'll just show it to you here. I have it here. I'll just open it. So this is, no, I will not install updates today. So this is a normal text file that can be opened using any text editor. I'm using Notepad++ in this case. And here you can see I have the file with the full path to the different DAT files, which I located here. And finally, the path for the output file. So that's just a normal text file that I then load into Res3DInv by selecting File, Collate Data into Res3DInv format. The next question is whether the coordinate system of the coordinates that you put in the 2D DAT files matter, or the reference system for the coordinates. And for this kind, just to create a 3D inversion, the reference system for the coordinates doesn't really matter as long as the relative position of the 2D lines is correct. However, it is assumed that it is a metric coordinate system like UTM coordinates or whatever. It can also just be a local coordinate system that you have defined on your field site. So if you don't have a GPS available or anything, you can simply define a local coordinate system by putting out a few spokes in the ground or something that you know where are. And another question I have received is whether the coordinates for all the electrodes are required. So you can see in this case, I have a coordinate for every 5 meters. So in this case, I have coordinates for all of the electrodes, but that it's not required. Actually, you can get away with only having the coordinate of each end of the profile. If the profile is completely straight, then this is perfectly fine. And you can also just have a few coordinates along the line, maybe 5 coordinates or 10 coordinates. That's plenty to define the position of the 2D lines, and then the program will interpolate the rest of the positions for you. And there are the answers I have had. Somebody is saying thank you in the chat. Thank you again. It's nice that you want to join and want to learn more about Res2DInv and Res3DInv. And remember that if you have any questions that arise after this webinar, you're also very welcome to send us an email. Then we'll try to answer them. And I can see that I get a few more questions now. The instrument put out its coordinates. Can it be used to get information of first and last electrode coordinates and then use it? So if you just have if you have an instrument with a built-in GPS, which just gives you the location of the instrument itself you have a problem because you only know one location, so you don't know the direction of the line. So you need at least 2 coordinates along the line. But if you're doing a roll along survey, for example, where you have the instrument placed at several locations along the profile, then it's fine. Then that is enough to define the profile. But you need more than one coordinate. I'll just look what the other questions I get are. Is it possible to insert coordinates using longitude and latitude, and how to replace the file text? So as I said, the coordinates have to be in a metric system. So if you have longitude and latitude, which is degrees and minutes and seconds, then you have to use a converter, and you can probably just plug the coordinates into Google and then get them out as UTM coordinates instead. But the program cannot do the coordinate transformation yourself. So the coordinates in the DAT file has to be metric. I'll see, maybe I'll just wait a few seconds to see if more questions ticks in, but otherwise you're very welcome to send the questions in an email, and then we'll put out a document in a few days with answers for all the questions, together with a recording of the webinar if you want to watch part of it again. And I think that you'll also automatically receive an email with the link to all of this, and otherwise you can find it on our webpage under webinars. Thank you very much, and have a nice afternoon.